right. Welcome to your second pre-recorded lecture. So this lecture will take a little bit longer and maybe a little bit more challenging conceptually compared to some of the previous content that we've talked about. So as we go through this lecture, I encourage you to not only just take notes, but also to take a moment to pause or take breaks as you need in order to fully digest the entirety of the content that we'll cover in this lecture. So of note here, we're going to do a lot of practice exercises in the next class for this particular topic area. So if some of it doesn't feel like you understand it, or if you have any questions, we can cover that at the beginning of that class so that you have more grounded knowledge to apply to some of the calculations you'll be doing during that exercises or during those exercises. All right, so in this lecture, we're going to begin to delve into the measures that we use to really quantify risk and associations. So first, let's talk about what exactly is an association. So ultimately, an association really just means that we see some type of pattern or some type of corresponding nature of two different factors. So for example, in this graph, we can see that as the per capita consumption of cheese, I know I've used a lot of cheese examples, so please forgive me there. That line is in green, and in the blue, we see the number of people who died becoming entangled in their bed sheets. So this is super correlated. They look like they're strongly associated, and that there might be a relationship between per capita consumption of cheese and people dying in their bed sheets. So that's a bit of a silly example. But when we think about associations, that's really what we're really trying to capture is the relationship between two different factors. Um, so an association is traditionally defined as a sort of statistical dependence between one or more events, some type of characteristics or other variables. Can also be referred to as a correlation. So I used the word correlation previously, which just means that two factors that you're observing are distributed in similar manners. And I want to caution you, and this is really, really important, that correlation and association, those aren't factors of causation. It just means that there's a relationship between two factors. So while our example earlier was a little bit sillier and kind of a no-brainer, some of these associations that we find in our research might be a little more insidious, or unexpected, or we might be drawing incorrect conclusions about what we're finding. So as an example, there's a heavy association between carrying a lighter and the incidence of lung cancer, but it's not a cause of lung cancer. Maybe it's due to the fact that people who carry a lighter may be more likely to be people who use tobacco. So there's something else going on there. So the associations that we find, they might be explained by a causal relationship, which is what we're ultimately trying to seek to find, but it could also be due to chance. So this is some type of random error, or it could be due to bias. And that's one of the things that we can really address in our study designs or in our analytic designs. So examples of that could be some type of systematic error in how we collected information, or who agreed to be observed in the first place. So when we look at measures of association, we're really seeking to answer questions about the relationship between an exposure and an outcome. We're trying to think about, is the exposure weakly or strongly related to the outcome? If we increase, or does the exposure increase the risk of a disease or an outcome? Is it a risk factor? So think of something like sunlight or radiation and its relationship to the development of skin cancer. So more exposure to sunlight or radiation could be a risk factor. Um, we're also seeking to answer questions like, does the exposure decrease the risk of a disease or outcome? So is it a protective factor? So it's something like social support, something that can help decrease the likelihood that somebody's going to experience something like postpartum depression. We also are looking to answer whether or not there is an association. So there might not even be an association between two different factors. So, some key things that we're really interested in finding by capturing the association between two different things, we're really looking at the strength or magnitude of a relationship as well as the direction, so positive and negative. Is it a risk factor or protective factor? So, to highlight again from our previous lecture, we talked about the weight of epidemiological evidence from a variety of study designs that we'll talk about later in the semester, and the role of descriptive epidemiology really laying the foundation for how we do analytic epi. So, we talked about using measures of prevalence, measures of incidence. So, in this lecture, we're going to talk about some of the metrics we use in analytic epi to quantify the relationship between different exposures and their associated outcomes. So, the goal of analytic epi is to determine whether or not two things are related. So, I keep using the word exposure. And what I really mean by exposure is some type of factor, characteristic, determinant that contributes to the development of some sort of outcome. So, an example of this could be like tobacco as an exposure for lung cancer as an outcome, or having unprotected sex with multiple partners as an exposure, and sexually transmitted diseases as an outcome, or like having the presence of the BRCA gene and the subsequent development of breast cancer. So we're really seeking to understand the relationship between two different factors, knowing that this one might be key in causing or being associated with the development of any type of outcome. So to do this, again, ultimately, our primary goal is to quantify and evaluate risk. So risk is ultimately the probability of some type of outcome happening within a specific period of time, or we could think about it as the likelihood that someone will develop a disease given a specific exposure within that time frame. So as we tend to think about things, we have this overarching definition, but always, 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 we have these sub definitions of broader ideas or concepts. So risk can be divided into a number of different concepts. So we have this idea of absolute risk, relative risk, and risk differences. So absolute risk is what we've really already talked about. These include our key measures of cumulative incidence and incidence rate. These measures help us to really identify the probability that somebody will develop a disease over a specific time. When we think about relative risk allows us to evaluate risk across two different groups. Typically, we're comparing the risk of disease in exposed and unexposed groups. So it's really a catch-all term that represents differences or ratios when it comes to cumulative incidence or the incidence rate. So we have the cumulative incidence ratio and the incidence rate ratio, which are all just incidence in the exposed and incidence in the unexposed. Absolute risk difference is pretty much exactly what it sounds like, and really quantifies the difference between one group and another group. An easier way to think about this as a comparison to, say, relative risk is that relative risk is a ratio of two different groups, and the risk difference is the difference between the two groups, which allows us to calculate or quantify the amount of excess risk posed by an exposure, which can be used both in public health and clinical practices. So later on in this lecture, we'll talk about attributable risk and population attributable risk. So going back to absolute risk. So absolute risk, as I just mentioned, is quantified by cumulative incidence or the incidence rate. So recall from the lecture we just had, cumulative incidence represents the number of new cases divided by the number of people who are at risk for becoming cases. We had this example before where we looked at attack rates. So remember, attack rates are a form of cumulative incidence specific to an outbreak. So in this example, I want you to take a minute to pause the video to try and calculate cumulative incidence among those who ate jalapenos. So in looking at the cumulative incidence or the attack rate of those who ate jalapenos during this particular outbreak, we had 54 people who ate jalapenos and became ill, and 65 people who ate jalapenos in total. So you have the people who became cases and the people who were at risk of becoming cases. So our cumulative incidence is thus 54 over 65, or 83 per 100, or 83%. So we interpret this as among those who ate jalapenos during this particular outbreak, 83 per 100 became ill, or 83%. The risk of illness of those who ate jalapenos was 83%. Incidence rate, as you remember, differs from cumulative incidence because it takes into account the amount of time that somebody is observed or contributed. Remember that cumulative incidence assumes that everybody was observed for the same period of time and contributed the same amount of time. So it's appropriate for fixed populations. So when calculating this, we're looking at the number of new cases divided by the amount of time people spent being at risk. So here we have an example of a study that looked at nurses between 1993 and 1999, where researchers captured the number of hours worked per week and then the incidence of diabetes. So to calculate the denominator, we add up across this row here the amount of time or person years that were observed among the 62,000 subjects that were observed. And then in this row, to get the numerator of the number of new cases that occurred during this time, we add up this row. So we get ultimately about 350,000 person years of time observed and 365 new cases of type 2 diabetes. So again, I want you to take a moment here to again pause the video and attempt to calculate the incidence rate of diabetes among the women observed in this study. So you should have calculated, if you had made the attempt, 365, which was the number of new cases of diabetes, and 350,000 as the amount of time of follow-up, or the amount of time people spent at risk. So we get 103.88 per 100,000. And we would interpret this as between 1993 and 1999, there were 104 incident cases of type 2 diabetes per 100,000 person years of follow-up among the women who participated in this particular study. Now we're going to talk about relative risk, and I want you to think about the word relative and what it really means. So the word relative really reflects a comparison between different groups. And oftentimes, when we're thinking about the risk of the disease and its relationship to various exposures, we want to think about the risk of an exposure on disease being relative to what would happen if that exposure or factor wasn't there. So you have some sort of framing to understand what that added exposure what kind of risk that it carries. So, because it's relative and we're comparing two different things, we use a ratio. So remember, this is one of our key metrics or common metrics that we use in epidemiology. And relative risk takes the ratio of risk in the exposed to the risk in the unexposed. So this could be risk when we think of cumulative incidence or our incidence rates between two different groups. And it's important to consider that these are captured within the same time interval. So because relative risk is a catch-all group that encapsulates risk ratios and rate ratios, there's a key difference in how these are quantified. So in your risk ratio, we're looking at cumulative incidence. So the ratio of incidence in the exposed versus cumulative incidence in the unexposed. When we're looking at a rate ratio, we're comparing the incidence rate in the exposed to the incidence rate in the unexposed. So let's look at a couple examples. So we have our jalapeno and foodborne illness example. So if we're looking at the incidence or the cumulative incidence in the exposed group, you've already calculated that. So to get the cumulative incidence in the unexposed, we do the same thing. So if our exposure is eating jalapenos, those who are unexposed are those who did not eat jalapenos. So you would take the ratio of the cumulative incidence or attack rate here and divide it by the cumulative incidence or attack rate here. So what that allows us to do is to test our hypothesis that jalapenos were the source of whatever the foodborne illness was in this outbreak. So you take the attack rate among those who ate jalapenos and the attack rate among those who didn't. So here's your cumulative incidence there that we calculated before, which was 83%. And you calculate your attack rate here, which gives you 30%. So ultimately, you might conclude that the cumulative incidence was 2.77 times greater among those who ate jalapenos. When looking at incidence rate, so we already calculated the incidence rate of those who, the incidence rate of diabetes in this sample. But say we wanted to look at those working less than 20 hours to those who were working 21 or more hours. So we would calculate the incidence rate among this group and compare it to this group. So in this, your denominator and your numerator are going to change because this would be the sum of this group and this would be the sum of those working 21 or more hours. So if we want to test the hypothesis that those who work more than 20 hours are at greater risk of disease, we would take and calculate the rate ratio. So what we get is among those who work 20 or more hours, the incidence rate is 344 new cases for every about 300,000 years. And then we have 21 new cases in our group that worked less than 20 hours per 55,000 person years. And what we get is 3.07. So what these ratios give us really allow us to establish the magnitude and the direction of the relationships between our exposure and our disease relative to each other. And this scale, thinking about magnitude, thinking about direction. When the risk ratio, rate ratio is 1, that means that it's essentially a 1-to-1 ratio, meaning that there's no relationship. When it is greater than 1, we know that there's a positive relationship. There is a risk involved with whatever that exposure is. So if you look here, this is definitely greater than 1. So working more than 20 hours could be determined to be a risk factor for type 2 diabetes. And the further that this gets from 1, the greater the magnitude When the risk ratio or rate ratio is less than 1, we consider it to be a negative relationship, or it can be a protective factor. So the closer this gets to 0 and the further from 1 that it gets, also represents a stronger magnitude of the relationship. So the magnitude is how far the risk or rate ratio is from 1, and the direction allows you to establish whether it's a positive relationship or a negative relationship. Okay, so we're going to delve a little bit more into risk ratios, rate ratios, to provide a different framework in your mind for how we might calculate these. So I'm going to introduce you to this idea of the 2 by 2 table. This is like epi gold right here. So you have your 2 by 2 tables, which are typically formatted where you have your disease or outcomes at the top and your exposure statuses on the left-hand side. So typically these are denoted by like O plus. So they have the outcome, or O minus, they don't have the outcome. Similarly, you have those who are exposed, or E plus, and those who are unexposed. And then in each of these groups, you typically just write the counts. So those who have the outcome and are exposed go here. Those who don't have the outcome but are exposed are here. Similarly, those who are unexposed and have the outcome, and those who are unexposed and who do not have the outcome. And typically you add these up to get the total population who are sick. So all of the people who have the outcome, you add these two up to get the total population of those who do not have the outcome or are not sick. So this whole group. Similarly, on this side, you have the total number of people who are exposed. And here you have the total people who are unexposed. Typically, we label these A, B, C, and D. So if we're thinking about our jalapeno outbreak, you have the people who were infected and became ill with salmonella in A and C. You have the people who did not contract salmonella here and here. Of those who were exposed, you have A and B, and those who are unexposed, you have C and D. So what really helps with this table, or using 2 by 2 tables, is to give you a very quick way to put people into these groups to calculate your cumulative incidence for each group. So to do this, you would calculate incidence of disease in the exposed group. So that would be A. So the number of people who developed the disease among the total population who were exposed. So you would take this cell, which we call A, and divide it by the total population exposed to get your incidence among the exposed. So thinking through this logically, how might you calculate incidence of the disease in the unexposed? So we would take the number of those who are unexposed who developed the disease and divide that by this total population here. So we calculate these, and then we can use that then to calculate our cumulative incidence ratio. So we have our cumulative incidence in the exposed and cumulative incidence in the unexposed. And that, my friends, is how we get our risk ratios. Another way to format this in your brain is to use a formula. Some of us prefer formulas over writing things out as long sentences. So if we were to use the 2 by 2 table, we would calculate our incidence, our cumulative incidence as A over A plus B. In the unexposed group, we would calculate it as C over C plus D, and then take the ratio of that to get our cumulative incidence ratio. So if I were to ask you to make a 2 by 2 table, say, for example, looking at the association between smoking and coronary heart disease, with the hypothesis that we're looking at being that smoking increases the risk for coronary heart disease. So we have a total sample of 8,000 people who do not have coronary heart disease between these years. Among them, 3,000 people smoked at baseline and 5,000 people didn't. So this adds up to our total population here. At the end of our study, 84 of those who smoked developed coronary heart disease, and 87 people who did not smoke had coronary heart disease. So many people don't like word problems, but what we can do from this information is extract it into a 2x2 table. So you have your 84 people here who developed coronary heart disease and currently smoke. You have your 87 people who did not smoke but developed coronary heart disease. And you can get these cells populated by taking from the totals that we know we have. So they said here that we have 3,000 smokers. So we know that we have 3,000 smokers and that 84 of them developed coronary heart disease, which means that 2,916 of them did not develop coronary heart disease. We had 5,000 people who were unexposed or did not smoke, and we know 87 of them developed coronary heart disease. So we can get this number by subtracting 87 from 5,000. So if I were to ask you to calculate the risk ratio here, we could calculate the cumulative incidence among those who were exposed, so those who smoked, and those who didn't smoke. So that ends up being 28 in the exposed group and 17.4 per 1,000 people in the unexposed group. So we take the risk ratio and calculate the incidence in the exposed and the incidence in the unexposed. So in the exposed group, we see that the risk ratio is 1.61. And then in our referent group, so that takes essentially the risk in the unexposed group to the risk in the unexposed group. So that's going to be 1 because it's the same thing. Okay, so moving on to relative risk in terms of looking at rate ratios. So here it gets a little bit more complicated because we're working to consider time. So instead of your A and B cells equaling this total cell of all the people in the population, because remember, rates do not, risk or cumulative incidence does not allow us to account for the amount of time that people contribute to a study. So this cell is not necessarily going to be equal to these two in a non-fixed population, but it's calculated in a similar way. So in this case, your incidence in the exposed group is A divided by the total person time. And your unexposed is C over the total person time in the unexposed group. And that gives you your incidence rate ratio. Let's go through an example there. So in a study from 2010 to 2018, you find 17 breast cancer cases among those with radiation exposure. For this study sample, you get 681.5 person years of observation. And then looking at the unexposed group, you have 121 incident cases who contributed about 10,000 years of observation time. So think about this, take a minute, pause, and try to work to calculate what the incidence rate ratio might be in this instance. So you would calculate this by taking 17 divided by the amount of time they contributed to get 249 per 10,000 person years. In the unexposed group, you would have 121 divided by the total person years to get 117 cases per 10,000 person years. To get your rate ratio, you get a rate ratio of 2.13. So how might you interpret this? So going back to thinking about what relative risk means in terms of comparing the risk in the exposed and the unexposed, when the relative risk, whether it's cumulative incidence ratio or the incidence rate ratio, if the value is greater than 1, that means that having the exposure increases your risk of developing whatever the outcome is that you're examining. If it's equal to 1, that means, again, that you have a one-to-one relationship. That means that having the exposure doesn't necessarily modify the risk of developing that disease or condition. If your relative risk measure is less than 1, that means that having the exposure decreases your risk of later developing the disease. So it's a protective factor. So greater than 1, risk factor; less than 1, protective factor. So going back to what we just calculated with smoking and coronary heart disease, we see a risk ratio of 1.61. So off the bat, what do you think the inclusion of smoking as an exposure, is it a risk factor or a protective factor for coronary heart disease? So we can interpret this as among those who currently smoke have a 61% increased risk of developing coronary heart disease than non-smokers among this particular study population. So we see 61%. So what this means is that because 1 represents the same risk, we would add anything on top of that as being the amount of increased risk. Sometimes that's harder for people to interpret. So you could also interpret this as those who currently smoke have 1.6 times increased risk of developing coronary heart disease. You can also say something like the risk of coronary heart disease is 61% higher. You can also say that they have 1.6 times the risk in compared to non-smokers. So you can see that there are a myriad of ways that you can interpret risk ratios, but I want to encourage you to be a little bit mindful when you're writing out your interpretations of any metrics and being as explicit as possible in the language that you're using, describing the population who's being examined, the time period of follow-up, the exposure, and the disease. So it's an important note here, because cumulative incidence is synonymous with risk, you can switch out terms like cumulative incidence for risk or replace risk with cumulative incidence because they're essentially synonymous. Okay, going back to our rate ratio interpretation. So we had a rate ratio of 2.13. So take a second to think about how you might interpret that rate ratio. So in this case, you could interpret it as the incidence rate of breast cancer among this particular sample population who had the exposure was 2 times the incidence rate in women who were not exposed to radiation. Or you could also say that they had 113 greater incidence. The incidence rate was 113% greater among the women who were exposed compared to those who were not exposed. Again, if 1 is our null measure, 113% would represent the difference between this and 1. So how do we interpret protective effects? Because they're not necessarily the same thing when the value of your ratio is above or below 1 compared to when it is above 1. So we know it's a protective effect, but how might you interpret a relative risk of 0.64? It's really hard to understand or wrap your head around what that would mean if I were to say the risk of disease is 0.64 times the risk of the unexposed group. You could instead say that the exposed group had only 64% of the risk, because again, you're taking the difference between 1 and the relative risk. Or you could instead subtract that from 1 to get 36%. So the exposed group has 36% lower risk of disease compared to the unexposed group. The one really important consideration that I want you to have just at the back of your mind is that our relative measures that we're using here are reciprocals of each other. So they might have equal magnitudes, but be in opposite directions. So this is really relevant when you're trying to compare two different relative risks, risk ratios, rate ratios, where one is below one. So you have a protective factor happening here. So by calculating the inverse of the one that is below one, so the protective factor, you can determine which one has the greater magnitude by putting them on the same scale. So because they're both on a multiplicative scale, you will be able to extract some of that information to determine whether or not the magnitude is the same. So let me give you another way to think about it. So because relative risk is on a multiplicative scale, you can calculate the strength based on the inverse. So 1 over the relative risk as the strength of the association to determine what it would be if that value was measured on the same scale. So putting either measuring both on the protective side or both on the risk factor side. So to compare, as an example, the relative risk of disease A, it being 1.67 in vegetarians compared to non-vegetarians, we find a relative risk of 67%. In disease B, we find it to be 0.60, or having only 60% of the risk, or 40% lower than the unexposed group. So if we were to try and evaluate what disease is more strongly associated with diet, we could take the reciprocal of the one that is below 1 to get 1.67. So both of these are exactly the same. So when comparing the magnitude of the relationship, we want to keep that in the back of our mind. Even if this one looks to be less than this one, we can put them on the same scale to make the comparison. Obviously, if both are above 1, you can easily draw comparisons between the magnitude of the relationship. So if one of these were 2 and the other was 3, you could say that the one that is 3 has a greater magnitude compared to the one with a value of 2. If both are measured as protective factors and you're comparing the magnitude there, you would just compare which one is further away from 1. Okay, to wrap this section up, when we interpret relative risk, here is essentially a sentence where I just want you to populate the important information when making your interpretation. So you would put the risk of whatever disease you're looking at among the exposed is whatever metric you calculated times the risk of disease among the unexposed over whatever time period your information was collected. Highlighting here that when the value is 1, we would consider that a null finding, meaning that the risk in the exposed group and the unexposed group is not different. Okay, so moving on to prevalence ratio. So this can be measured almost the exact same way, looking at prevalence in the exposed group and prevalence in the unexposed group. So going back to our 2x2 tables here, the way that we're going to calculate this is going to be the same. So A over A plus B and C over C plus D. So this is very similar to relative risk, but because it's prevalence, it's not risk. So it's very distinctly the prevalence ratio. So when thinking about the ratio of prevalence among the disease in the exposed and the unexposed groups, say we wanted to calculate it for whatever disease that this is, let's call this disease Y. So if we were to calculate the prevalence ratio, we would get, say, 12 over 17 divided by 8 over 23 to get 2.03. So if we were to apply some of the same findings that we had, or some of the interpretations that we had when we were considering our measures of relative risk, we would interpret them in similar ways, but we would use different language. So instead of saying risk in your interpretation, you would instead talk about prevalence. So the prevalence is 2.03 times greater in the exposed group than the unexposed group. So here we can use the prevalence ratio to calculate across the number of groups. So if we wanted to look at obesity among those age 30 to 44, we would take the number of obese cases divided by the total population. To calculate the prevalence here, we would take the group of obese cases out of that sample size. If you want to compare multiple groups, so in most cases, or in the cases we've looked at before, we had a 2x2 table comparing two different groups. But if we want to frame, say, the youngest age group, because we believe that age is important in this instance, we might consider just using them as our unexposed group, allowing us to compare each age group with the youngest one. All right, so that was a quick overview of prevalence ratio, and I'm open to taking questions in the next class that we talk about this. So I'm going to shift gears from relative risk to talk about attributable risk, or the risk or rate difference. So this is going to differ from relative risk because we're not taking a comparison relative to some unexposed group or some baseline. Instead, we're going to calculate the actual difference between two risks or rates. So attributable risk is really one of the more preferred ways that we can measure the impact of some type of public health program, activity, or clinical activity, and really represents the amount or proportion of a health outcome, whether you're looking at cumulative incidence or incidence rate, that is specifically attributed to a specific exposure. So notably here, we cannot use any data related to prevalence. This is purely specific to cumulative incidence and incidence rate because we are capturing risk. So we use this information to then calculate what proportion of a disease we can prevent if we were to just eliminate that exposure entirely. So we use that by calculating the number of cases that are attributable to that particular exposure. What this implies, however, is that there is a causal relationship between the exposure and the disease, which is something we'll talk about more throughout the semester, and some of the drawbacks to assuming a causal relationship between different exposures and diseases. So there are two main types of attributable risk. You have attributable risk and population attributable risk. So in attributable risk, we're looking at among those who are exposed, how much of that particular disease can we attribute to that specific exposure that we're looking at? Or how much of the disease can be prevented or eliminated if that exposure is removed? When we're thinking about population attributable risk, we're thinking about how we take some of that information and applying it to a broader population. So what we're measuring is in the total population, how much of that disease can we attribute to a specific exposure? And how much could we ultimately prevent in a broader population if that exposure is eliminated? So similar, but this one, population attributable risk, is a little bit more broad. So when we look at incidence in the exposed and the unexposed and are looking at the risk difference, we assume that you have this sort of background or underlying risk for the disease because some of the unexposed group ends up with the disease. So the risk difference really is calculating the amount that we assume to be associated to the exposure. So to answer the question or how to calculate it, what we're looking for is taking the overall risk for disease in that exposed population and subtracting the background risk. So we're taking this whole thing in the exposed group and subtracting this purple part. So taking the incidence in the exposed group minus the incidence in the non-exposed exposed group to get the attributable risk. So simple subtraction. Conceptually, it's a little bit more challenging to wrap your head around. So going back to our example about smoking and coronary heart disease, we calculated the incidence among those who smoked and among those who didn't smoke. And we calculated a risk ratio of 1.6. And that we calculated in this way. So we get the relative risk, but let's look at the risk difference. So if we wanted to calculate attributable risk, we take the incidence in the exposed and subtract incidence in the unexposed. So instead of taking a ratio, you're subtracting them. So what you end up with is the incidence in the exposed minus the incidence in the unexposed to get 10.6 per 1,000. And how you might interpret this is that among smokers, there are 10.6 cases of coronary heart disease per 1,000 people that is attributable to smoking. Or you could say that among smokers, 10.6 coronary heart disease cases per 1,000 would be removed if smoking was eliminated. So let's take that and make it a percent. So we calculate attributable risk percents to answer questions like what proportion of the risk for disease in the exposed persons is due to the exposure. So instead of saying that this number of cases is due to the disease, we're going to look at the proportion of risk that exposure adds to the disease. So remember, we calculate our attributable risk by taking the difference between the exposed and unexposed group. To get the attributable risk percent, we calculate the risk difference and then divide it by incidence in the exposed group. And then we multiply it by 100 to get a percentage. So in our example here, we have our risk difference divided by the incidence in the exposed, multiplied by 100, and that gives us 38%. Again, we'll be doing some calculations in class that'll make it a little bit easier for you to wrap your head around, because this is something that is much more easy to do or understand when you're applying it to an actual scenario. So how we might interpret our attributable risk percentage is that 38% of coronary heart disease in smokers is attributable to smoking, or 38% of coronary heart disease would be removed if smoking was eliminated. So we're going to pivot to population attributable risk. So again, thinking about this less in terms of exposed and unexposed, but how we can apply that knowledge or background foundation in understanding attributable risk and applying it to a broader population. So looking at a total population, we want to know how much disease we can attribute to a specific exposure. This helps us really to anticipate what the benefit would be to removing a particular exposure. So this could be this has very clear implications for public health policy and programs because it provides information about excess disease in the entire population, not just among those people who are exposed. So obviously there's a clear distinction, but a very clear difference between attributable risk and population attributable risk. So attributable risk is the proportion of the disease among the exposed that is due to the exposure. And we know that we could remove or eliminate this excess if the exposure itself was removed. When looking at the population attributable risk, we're looking at the proportion of the disease in the total population that is due to exposure, and that this excess disease could be eliminated if the population if the exposure was removed. So we know that the total population is typically some sort of combination of exposed and unexposed. So we know the incidence is going to be somewhere in between here. So typically we don't know the total population incidence. So we're going to have to calculate it, and we can calculate it knowing the incidence of the disease in the exposed and the incidence of the disease in the unexposed. But here is where prevalence comes into play. So if we want to know incidence, we can apply some of these measures of incidence and include consideration of the prevalence in the total population. We can calculate the total population incidence. So keep in mind that this total population incidence is typically some type of weighted average of the incidence from the exposed and unexposed groups, which could be determined by the distribution of the exposure within that particular population. Okay, so this can be a very challenging metric to calculate. But we'll walk through it here and how we can integrate our knowledge of incidence in the exposed and unexposed and integrating our knowledge of the prevalence. So we can calculate or estimate incidence in the total population by multiplying the cumulative incidence among the exposed by essentially the prevalence. So that's the percent exposed in the population, and adding that to the incidence among the unexposed multiplied by the prevalence in the unexposed. So we can calculate that by taking 1 minus the prevalence of the exposed. To simplify this, we would have incidence in the exposed multiplied by prevalence of the exposure, and adding that to the cumulative incidence in the unexposed multiplied by 1 minus the prevalence of the exposure. So let's take what we've just learned and apply it to our example looking at smoking and coronary heart disease. So we've already calculated our incidence in the exposed and our incidence in the unexposed. Say we get data from another place, and that gives us the prevalence of the exposure or smoking in the total population, which is 44%. The key here is that you're not looking for prevalence in the disease or of the disease, you're looking for prevalence of the exposure. So using this data, we can use our formula or apply our formula to calculate the incidence in the total population by taking our incidence in the exposed multiplied by the prevalence of the exposure in the total population and adding that to incidence in the unexposed and multiplying that by 1 minus the prevalence of the exposure. So this is giving us the prevalence of the not exposure, which we could calculate because you have 100% of the population, and if 44% of them smoke, we know that whatever the difference is between 1 and 44 is the prevalence of the not exposed, the non-exposure. So then we would run our formula and get something like 22.1. So we would interpret that by saying something like the incidence of coronary heart disease in the total population is estimated to be 22.1 per 1,000. So remember, our incidence rates that we applied here are out of 1,000 or per 1,000 population. So that translates down to how we calculate or estimate incidence in the total population. So to keep yourself sane and to make sure that your estimate of the total population is correct, we know that the cumulative incidence in the total population should be somewhere between those who are exposed and those who are unexposed, with those who are exposed having the highest incidence and those with the without the exposure having the lowest incidence. And because the total population is essentially a weighted average of what we expect to be in the population at large. So here's a graphic representation. We know that somewhere in between the exposed group and the exposed group, that is where our population incidence will be, because you have some who are exposed and some who are not exposed. So what we calculated to be 22.1 previously does lie somewhere between 17.4 in the unexposed group and 28 in the exposed group. So in calculating our population attributable risk, we are seeking to answer the question of how much of the total risk of a disease is due to the exposure in a broader population. So you do this again, using simple subtraction after applying some complicated formulas to get some estimates to get the difference between the overall risk for disease in the population minus the background risk for the disease. So the incidence in the total population minus the incidence in the unexposed group. So in this case, we calculated or estimated our total population incidence to be 22.1 per 1,000. And in our unexposed group, we calculated it to be 17.4. So our population attributable risk then becomes 4.7, which is the difference between this and this. We could interpret this as among the total population, 4.7 cases of coronary heart disease per 1,000 population are due to smoking, or 4.7 cases of coronary heart disease would be eliminated if smoking as an exposure was eliminated from the total population. So there are multiple approaches to this. So here is a second or alternative approach to calculating population attributable risk. So in this case, we can estimate the risk in the total population and the risk of among the unexposed. We can calculate this instead by taking what we've calculated to be the attributable risk and multiplying it by the prevalence of the exposure. So in examining this relationship, we've calculated the attributable risk here in the population as we did previously. And then we take that prevalence that we recently discovered and multiply it by our attributable risk. So again, our attributable risk is incidence in the exposed minus incidence in the unexposed. And then we multiply this by the prevalence of the exposure, so 44. And that gives us 4.7 cases per 1,000, which is the same answer we got through the first method. So we can interpret this by saying, again, that among the total population, 4.7 cases of coronary heart disease per 1,000 people is due to smoking, or would be eliminated or would be removed if exposure to smoking was eliminated from the population. Okay, so one of our last metrics today that we're going to talk about is population attributable risk percent. This gives us the proportion of the risk for a disease in the total population that is due to the exposure. And we calculate this by subtracting incidence in the total population minus the incidence in the unexposed group and dividing that by incidence in the total population. And again, multiplying it by 100%. Or PAR divided by the incidence in the total population. So we get this by taking what we've calculated before to be 22.1 minus incidence in the unexposed divided by the incidence we estimated to get 4.7 over 22.1 and ultimately 21.3%. So we would interpret this as 21.3% of coronary heart disease in the total population is attributable to smoking. Or if we remove smoking, we could eliminate 21% of excess deaths. So let's summarize some differences between population attributable risk and population attributable risk percent. So we know that because population attributable risk will always be somewhere between risk in the exposed and risk between the exposed and the unexposed, we know that attributable risk or population attributable risk will always be less than attributable risk and the attributable risk percent because it's a weighted average that includes consideration of the unexposed group. So when we examined our attributable risk among the exposed, it's higher when you're just looking at the exposed compared to what you expect in the total population. Similarly, when you're looking at the percentages, the attributable risk percent is greater than what we see in the population. So again, to reinforce this or to say it again more clearly, we know that the population is some combination of the exposed and the non-exposed. So it's going to be some type of average between these. So population will never be greater than the exposed or less than the unexposed. Okay, so why do we use this information? Well, why is it important? So calculating the attributable risk among those who are exposed allows us to quantify any potential for risk reduction if that particular exposure is removed. It has a lot more clinical applications because you're focusing on a discrete group of people, typically patients or some sort of more closed or fixed population. Public health seeks to address these issues at a broader scale. So we apply things like population attributable risk to help quantify the potential for risk reduction of particular exposures, so that we can not only communicate the impact of a disease, but also evaluate efforts or quantify the impact we could have if we address particular exposures. So there's some key considerations when we're using measures of attributable risk that I sort of alluded to earlier. One is this underlying assumption that the exposure is the one true cause of the disease. And sometimes it doesn't allow you to consider other potential factors or confounders that might sort of interrupt or have an impact on the association that you've observed. You also want to consider when applying this information, can the exposure be reasonably eliminated? How much would it cost to do? What are some of the political, commercial barriers to doing some type of clinical or public health application that might make um, eliminating the exposure nearly impossible? So consider in the back of your mind, thinking through implications of using attributable risk. If you are thinking through the amount of a disease that's there. So how many cases of a disease can be prevented if a disease is, or if an exposure is eliminated? If your attributable risk is high, but there is a very low chance that the exposure is happening, eliminating that exposure will only have sort of a minimal benefit. If attributable risk is low, but the exposure is very common, then eliminating that exposure will have a much larger benefit. So be very mindful in your interpretations or how you might apply what you learn from these measures of attributable risk and thinking about the further downstream implications of what information you're gathering from these particular metrics. So let's summarize some of the many metrics that we talked about today. So recognize this is a lot, and I just want to remind you that we will be putting these into practice during class time. So if there are aspects you don't understand, again, please reach out to me, ask questions. Feel free to leave some comments in the homework so that we know how this went. But to summarize, we have measures of absolute risk that we went over today. So again, cumulative incidence and incidence rate. We talk about measures of relative risk, specifically looking at the cumulative incidence ratios and incidence rate ratios. We talked about prevalence ratios, which are distinct in that they don't measure risk. Remember, keep that in the back of your mind, that prevalence doesn't allow us to capture measures of risk. We talked about attributable risk and population attributable risk. So there are a couple additional slides that are included that I won't go over here, but can be useful resources that include just a list of different ways of interpreting some of your metrics that you've calculated or some of the formulas. Also on Canvas, we have a list of all the formulas used to calculate these. You can use as a reference especially during the in-class exercise. So thank you guys. This was great. I hope you had a lot of fun calculating stuff or learning about these different measures of risk and measures of association. And so I look forward to working with you in class to try and implement these.